have so far to go. Okay, so we're looking at an entropy example here. This will be looking primarily at this idea of like an entropy or a chaos, a delta S. That's what we're going to be kind of looking at here. Now, for our example, this is the setup. We have 50 kilograms, I know, that's a lot, of water. And this water is at 20 degrees Celsius. We then have 50 kilograms of, you guessed it, water, but it's going to be at 24 degrees Celsius. So what we're going to do here in this problem, we have equal amounts of water at 20 and 24 Celsius. We're going to mix them together, okay? Now, if we wanted to, we could go back to what we know about calorimetry and all of that nonsense, and we could find an equilibrium temperature. But we already know the equilibrium temperature here. If we have equal quantities of the same material and we mix them together, we're going to split that temperature halfway down the middle. So the 20 is going to go to 22, and the 24 is going to come down to 22 as well. So these are all going to equal out 22 degrees Celsius. What we are trying to figure out, though, in the problem is, what is the change of entropy in this system? Now, a naive look at this may say, well, if we're heating up the cool water by 2 degrees, and we're cooling down the hot water by 2 degrees, and it's the same amount, hey, they're both changing by the same amount. We should have 0 change in entropy. But that will be wrong. We've already talked about in prior videos that the only way we're going to get 0 change in entropy is if nothing happens. So we're going to get some positive value here, but let's try to figure out why. We know that a delta S, a change in entropy, is equal to a Q, some heat, divided by an average temperature. And in our scenario here, we're actually going to have 2 changes of entropy. We're going to have a delta S for the cooler water and a delta S for the hot water, the 24 degrees Celsius. And it's only these 2 delta S's added together that will give us our total change of entropy of the system. So we need to find both delta S's and simply add them together. Well, to do this, and let's do this for the cool water first, we're going to have some Q over an average temperature. Well, the Q for this, we have to go back to calorimetry for, and we know that our Q here is going to be equal to an MC delta T. And if you've never seen that equation before, then go back and watch our calorimetry videos. Because what this just shows us here is we'll have the mass of the water, 50 kilograms. Our C here, or the specific heat of water, will be 4,186. Normally we use the 4.186 value, but that was when we were in grams. Because we're in kilograms now, we need to put that more zeros onto it. We got to blow that up into the thousands. But then our delta T here is just going to be 22 minus 20, and we're just going to get a 2 degrees Celsius. We still have to divide this by an average temperature, but let's hold off on that for a second. If we go and do the same thing down below for the hot water, Q over T average, we're going to get MC delta T, and that's going to be the 50 kilograms of water of 4,186, because we're in kilograms, because that's the specific heat of water. And then in this case, our final minus initial is 22 minus 24, which gives us negative 2. And this will be divided by some average temperature as well. Now, when we look at this, yeah, we're like, these are the exact same tops, the exact same numerators, but one's positive, one's negative. Shouldn't it be 0? No, it's not going to be 0. Stop thinking that. We are going to have 2 different average temperatures. When we think about the average temperatures, we need to think about the cool water and the hot water independently. Our cool water went from 20 degrees Celsius to 22, which means the average temperature for our cool water was 21 degrees Celsius, which we are going to properly convert into Kelvin. So we're going to take 21, add 273 to it, and we're going to get 294 Kelvin. Our hot water, though, it went from 24 to 22. Its average temperature then was 23. Converting that to Kelvin, adding 273 to it, we get 296. The numerators here are different. Because of that, we are going to have two different values. Furthermore, when we go ahead and we add these together, the hot water with that denominator of 296, that's a larger denominator than the cool water, which means that hot water value of delta S is going to be smaller than the cool water, which means when we add the positive and then we add the negative value to it, we're going to be left with a positive amount. When we do this, we're going to have 4.186 times 10 to the 5th divided by 294 plus a negative 4.186 times 10 to the 5th divided by 296. Remember, do these divisions first and then do that subtraction. When you do this, you get a value of approximately just 10 joules per Kelvin. And that is our change of entropy here. Notice how it is positive. When we get a delta S that is a positive value, this means that we have added some heat to the system. We have heat in. When we have a delta S that is negative, this means we've taken heat out of the system. This would be like for a refrigerator. But note, even if your delta S is negative, that might be for a small system. That means you just use something else in the environment to do that. And globally, on a universal scale, your delta S will still be positive. Okay? But that's how we approach a problem like this. We look for our two delta S's. We recognize our temperature averages are different for each of them. And we add them together. We should see a positive change in entropy. But with that, this problem is finished. That's actually the last thing we're going to talk about for this class's unit on thermodynamics. That's not the end of thermo. There's so much more, but that's going to be what we're going to end with in the AP Physics 2. The other videos that exist for this are all related to intergalactic problems and trying some really weird, complicated things out as kind of like homework and practice. So make sure you check out those videos if you haven't. And if you need any help, just feel free to contact me. But until next time, adios, and take it easy.